Now, what we will do now is try to do a steady state analysis of a general converter. So, of course, what is the intention is, I mean, though we have not studied very general converter, we have studied, I mean, in detail only one particular converter, but in the same converter we have tried to do analysis for different modes. Okay. Now, there is a possibility of doing a steady state analysis of a general converter which is applicable for any mode. So, we will see how to do that and try to see how one can apply it to special cases. Steady state analysis of a general line commutated converter. So, so far our analysis has been restricted to one particular circuit where we have 3 legs or 6 valves, and on the AC side there is a 3-phase voltage source connected in Y and 3 inductances, on the DC side a current source. Okay. Now, there can be some deviations from this. I mean, there can be more complexities. For example, there can be a resistance on the AC side in addition to inductance. On the DC side, instead of a current source, there can be a voltage source in series with an inductance, or voltage source in series with an inductance and resistance. Now, these complex cases are not as easy to analyze as we did till now. So, what we have considered till now is a very simple circuit. A current source on the DC side and a voltage source with inductance on the AC side is a very simple circuit. There can be more complicated circuits for which it is not as straightforward as in the easier case to get the steady state analysis. But what we will do is, it is not necessary to take each and every case separately and analyze. We can do a very general analysis and apply it to special cases. Okay. So, what we will do is, we will try to first of all use some notations. T is the notation used for the period. This is in seconds or milliseconds. T is the period of AC voltage or AC side voltage. We already used this notation P, lowercase p, for pulse number. So, for the circuit that we studied in detail, this pulse number P is 6. Okay. So, we will consider another value of pulse number, that is 12, much later in the course. Then we define T with a subscript 1 as T by P. Okay. So, if T is period, what is T1? I mean, period divided by pulse number, what does it give? There is a name for that. What is it? Say, in the previous case, P was 6. So, if the period is divided by 6, what we get is T1. What is that? We have been calling that as, we have been using this name interval. So, if T in degrees is 360 degrees, P is 6, then 360 by 6 is 60 degrees, that is interval. Okay. So, T1 is the interval, but now what we are trying to do is, we are using some notations which is corresponding to the period or interval in terms of time instead of angle. Okay. Then there are this okay, let me write this. This corresponds to one interval. So, each interval has 2 subintervals. Has 2 subintervals. Now, the first subinterval, we used to take the first subinterval as starting from alpha. So, if I take the independent variable as angle, that is omega o t, then it is alpha. If I take time, then it is alpha by omega o. Okay. Then I will call the other end of the first subinterval as alpha by omega O plus T1. So, this subinterval corresponds to conduction of m plus 1 valves. Then the second subinterval starts from alpha by omega O plus T1 to what? To what? Alpha by omega O plus uppercase T with a subscript O. Okay. Now, this corresponds to conduction of how many valves? M valves. Now, I use a general notation m plus 1. I mean, that is because this is applicable even if I take one particular converter, 6 pulse converter which we have already studied. It can be 2 and 3 valve conduction mode or 3 and 4 valve conduction mode. So, if it is 2 and 3 valve conduction mode, m is 2. If it is 3 and 4 valve conduction mode, m is 3. Okay. Of course, this T1, it is obvious that it is less than or equal to uppercase T1 and greater than or equal to 0. Now, if I take the first subinterval, see, please note that in general it can be shown that the circuit is linear. So far also the special cases that we considered, whether it is 2 and 3 valve conduction mode or 3 and 4 valve conduction mode of the simple 6 pulse converter that we studied, it is a linear circuit. So, the equations governing the system are linear differential equations, and not only that, they are linear with constant coefficients as well. So, there is a difference between linear constant, linear time invariant system, linear time varying system. So, the equations that we come across in this course are linear time invariant. So, for which the solution is straightforward. Okay. Now, before going to the equations that govern the circuit in the two subintervals, I will use some more notations. X1 is the notation used for state vector in the first subinterval. X2 is the state vector in the second subinterval. Now, can we say anything about the relative sizes of x1 and x2? See, state vector can be considered to be a column vector, can be considered to be a column vector or a column matrix. So, what about the relative size of x1 and x2? Which one is larger first of all? x1 is larger or x2 is larger? Both are same. See, based on our understanding of some special cases so far, if I take 2 and 3 valve conduction mode or 3 and 4 valve conduction mode, if you look at the first and second subintervals, you see that the number of loops is larger in the first subinterval, it is smaller in the second subinterval, and the difference is 1. Now, it so happens that it can be shown that x1 is of course larger in size compared to x2, and it is larger by 1. So, the number of state variables in x1 or in the first subinterval is 1 larger than the number of state variables in the second subinterval. Now, that means the state variables in the second subinterval are also state variables of the first subinterval, but one of the first subinterval state variable is not a state variable of the second subinterval, because there is one valve current which goes to 0. So, there is one valve current in x1 which is not appearing in x2. Okay. So, we will say that state variables. See, state variables are nothing but the elements of the state vector. So, state variables in x2 are also state variables in x1. So, one state variable which can be considered to be one of the val current, val current can be considered as a state variable. That val current which goes to 0 in the first subinterval can be considered as the state variable which is there in x1, but it is not there in x2. Okay. So, we say the outgoing valve, see, outgoing valve means the valve which stops conducting, the outgoing valve current actually becomes 0 at what instant? At t equal to, see, for the time being I am trying to write equations with independent variable time. It becomes obvious why I am switching to time, it becomes obvious quickly. At alpha by omega O plus T1. Okay. So, the outgoing valve current becomes 0 at this instant alpha by omega O plus T1, and it is a state variable of x1, but not a state variable of x2, and it is in x1. It means what is in x1? The outgoing valve current is in x1 and not in x2. Okay. So, I can try to write what are known as differential equations. So, if x1 and x2 are the state vectors in the two subintervals, there are two different sets of differential equations corresponding to the two subintervals. So, these can be shown to be linear time invariant equations for which the solutions are straightforward. So, we will try to write the equations, the solution, and then what we will see is we will know everything in this except for one particular quantity that we are solving for. Okay. So, I will not give all the answers right now. So, I will stop at this point. We will continue the analysis of this in the next class.